extreme physics.
All right, let's take a look at the 2015 free response question number 3. It's a rotation problem. We got a uniform thin rod of length L and mass M allowed to pivot about its end as shown in the figure above. Using integral calculus, derive the rotational inertia for the rod about its end and show its ml squared over 3. Well, good. They gave you the answer in case you couldn't actually solve it. All right. Well, let's review how to. This is in your notes. I'm not going to spend too much time on this. Is in your textbook. We got that. We want to rotate it about its end. Here's our thin rod. Here's our dm. There's our little infinitesimal mass. And this width, of course, is dx. All right. So we're going to use integral calculus. The integral of r squared dm is the moment of inertia. So we just need to get this dm in terms of dx. And probably the easiest, and this is length L. So this is position L here. So the little mass divided by the little length, that would be kilograms per meter. And that would be the total mass, which is m divided by total length. Right? So there we go. So dm equals m over L dx. All right, let's just substitute that in here. We're going to integrate across x instead of r because we're not integrating up in any direction. We're just going straight out. So we're going to go x squared m over L dx. Just substituting this into here. And we're going to integrate from 0 to L. 0 to L. And what do we got here? We got m over L x cubed over 3 from 0 to L. And we got m over L. L cubed over 3. Boom. It becomes a 2. And we get m L squared over 3, which is what we were looking for. Beautiful. All right. There we go. Make sure you can find the moment of inertia of a thin rod using integration. Derive an expression for the velocity of the free end of the rod at position B. It's going to fall. All right. So we got a rod here. Going to start like that. It's going to fall down to here. They call that position A. And they call that position B. Derive an expression for the velocity of the free end of the rod. All right, so really what we're going to do is we're going to find the rotational speed of this thing, and we're going to use it using conservation of energy. It's the only reasonable way to do it. You really couldn't use Newton's laws because the acceleration keeps changing, so that would be really difficult to do. So we're going to use conservation of energy. And I think we will, and so we got a center of mass here, which is right in the center, and the center of mass is going to fall, right? And this change in gravitational potential energy will end up as rotational energy. So let's do our basic energy statement. Energy at A equals the energy at B, and mechanical energy is conserved here. They didn't mention anything about friction or anything like that. But anyways, so this thing's going to fall, and then we're going to have a rotational speed. And then we want to know the speed at the end of the rod. Well, that'll be easy enough to do. The speed at the end of the rod will equal omega L, right? Omega L will be the speed around the end of the rod. All right, so let's see what we got. I'm going to call this zero gravitational potential energy when it's at that position. And so we end up with the gravitational potential energy at A equals the rotational kinetic energy at B. This thing isn't translating. It's strictly rotating around its hinge. So we get mg HA, and this right here is HA. From here to here is AHA. Equals 1/2 I omega B squared. All right. Well, HA is this is L, this is L over this is L, this is L over 2. So this is mg L over 2 equals 1/2. What did we say that was? ML squared over 3. And we know that omega equals V over L. So we go V at the end. I just put V. V over L squared. Alrighty. Well, these are going to cancel. And we end up with, and so is the mass. So what do we got? GL over 2 equals 1/6 V squared. All right. So it looks like V equals the square root of 3GL. All right. So what do we got? We got, that's what we get. So V equals the square root of 3GL. All right. Derive an expression for the velocity of the free end. There it is. This is B. 3GL. All right. An experiment is designed to test the validity of the expression found in B. How could it possibly be wrong? A student uses rods of various lengths that all have uniform mass distribution. The student releases each of the rods from horizontal and does some experiment. There's our data. All right. So they got some data, and they got some lengths and velocities. And it says, indicate below which quantities should be graphed to yield a straight line whose slope could be used to calculate the numerical value for the acceleration due to gravity g. What are you going to put on the horizontal axis? What are you going to put on the vertical? All right, so I got this. Well, you can do it a couple ways. I think what I would do is go back to this. I would say V squared equals 3GL. And then I think I would graph V squared versus L. And then this would be the slope, because this would be linear in terms of V squared L and V squared versus L. And the slope would be 3G. So this should give me a straight line, and whatever the slope is, I'll need to calculate the slope, and that will be that'll give me a value for G. All right. Well, I got to kind of do this on paper. So let's see what we got here. Before we do that, we get a value for G. This says describe 2 ways. We're going to get a value, and I'm sure it's going to be a little off. Describe 2 ways in which the effects of air resistance could be reduced. Well, you could use denser material, right? You could use denser rods. That way the force of gravity would be greater relative to the wind resistance, and that would minimize it. And the other thing you could do, I guess, is use thinner rods, or more aerodynamic rods, thinner rods, or something like that. There's 2 that's what I would choose if I was going to do it. All right, here's my graph, and as you can see, I plotted V squared versus L, and I drew a line of best fit, and I chose 2 points, calculated my slope, and I got 25.9 meters per second squared, and that is 3 times G, so therefore I got a G of 8.6 meters per second squared.
Extreme. Further.